Hello, everyone. Today I'll be talking to you about a specific class of convolutional neural networks known as the Temporal Convolutional Network, TCN, and how TCN is nowadays being utilized in several experiments related to EMG pattern recognition and its comparison against traditional classifiers. So let's dive in. The idea over here is that CNN has been utilized for a long time for modeling spatial relationships. But for sequence modeling tasks, we needed a different version of CNN or of convolutional networks in general that can be actually suitable for modeling sequences or time series data. So what the researchers have done, they instantiated this version or class of, let's say, convolutional neural networks known as TCN, the Temporal Convolutional Network, with an architecture that allow you to look at the temporal dependencies within the time series or within the signal that you are actually considering, in a similar fashion like LSTM or GRU. So it has been shown that convolutional neural networks can match the performance of recurrent networks on typical sequence models when using TCNs. So the benefits of using TCNs include, for example, better parallelism, better control over the receptive field size, and I will explain to you later on what do we mean by receptive field size. There's also the better control of memory footprint of the network during training and the more stable gradients. So you don't have issue with the vanishing and exploding gradients that you typically see with GRUs or like recurrent neural networks in general. Let's have a look at the one-dimensional convolutional network. So imagine that you have a time series, as you can see over here, or let's say a tensor or vector in general. Let's just refer to it in terms of tensor. So if you have a tensor, as you can see over here, the length of this time series, or the input tensor, that like basically it's a time series, we are calling it a tensor. So the length of this time series is denoted usually as the input length. The whole idea over there is that in a similar fashion, like you employ CNN networks, like the convolutional neural networks, when you do image recognition tasks, where you have filter and you move that filter across different parts of the images, you do the same thing over here. So you get a kernel of specific size. So over here, this is the kernel, or this is the filter for which you need to optimize the weights, just like a normal CNN network. And you define the kernel size or filter size. So in this example, as you can see over here, the kernel size is actually made of 3 samples. So your kernel or the filter should actually be also made of 3 samples. The idea over here is that you multiply the 2 of them together, so your filter weights by the time series values or the actual values in your input tensor, and the result of this dot product multiplication is the corresponding output value. And that is actually placed in a tensor that is denoted typically as the output tensor. So what you have over here will be an input tensor of the TCN, and this has a shape of batch size, input length, and input size. So input length and the input size. So as you can see over here, the input size is 1, but there could be more than 1 dimension, and I'll explain what that means to you in a second, basically in the next few slides. On the other hand, you also have a output tensor, and this also has a size of batch size. Input length, again, has to be the same input length size and an output size. Now, in the univariate case, where you only have 1 channel or 1 dimension, the input size and the output size, as you can see, will be equivalent. Both of them are equal to 1. But in the general multivariate case, where you have more than 1 input channel, the output size might actually be different from the input size, depending. Like, do you want to forecast just 1 variable or do like classification? What do you want to do exactly? Depend on the problem that you are currently looking at. So let's take it step by step and start going into more details. So moving forward, you will notice in many blogs or in many papers, they don't actually include the kernel over there when they do multiplication. So they imply that there is a kernel and there is a dot product multiplication. And for you to move from the input to the output, you are actually let's say, doing some sort of implicit multiplication by the kernel weights. So what happens over here typically is that we can see that to compute one element of the output, so if you want to compute this green element of the output, you look at a series of consecutive elements defined by the kernel size from the input. So if I want to compute the green value over here, I have to look at a series of values, which is defined by the kernel size. So in this case, kernel size is 3. I will consider 3 values, 1, 2, 3. And you can see that there are arrows going from the 3 values to the output value in the tensor and the output tensor. So to get the next element, you just usually shift either to the right or left, depending on what sort of illustration you are looking at and where is your beginning and ending. So in this case, there is another value over here. And for that one, you slide your arrows by 1 because you have a stride of 1. So stride over here means the window increment, let's say, as we explained in the previous videos. So you have a certain window size and you have a certain window increment or the stride. How much do you push by to go to the next analysis process? So over here, you have a kernel size of 3 and a stride of 1, which means I will fill this value by looking at 3 values. And then to fill the very next value, I will shift my arrows by 1 and then move forward or like in the other direction, depending on where you're looking at it, left to right or right to left, basically. Doesn't matter. Now, what happens if you have multiple input channels? And how could you have multiple input channels? To explain this, let me just draw something for you. And I hope my drawing will be better than in the previous videos because I always have issue with drawing somehow. I don't know why. So let's imagine that this is someone's hand, thumb, index, middle, ring, and the little, very ugly hand, but will do for our purpose. Let's imagine that there are 2 sensors located, on your forearm. Each one of these sensors will actually give me a time series. So the first one will give me some sort of time series. Let's imagine that this is my EMG signal from that time series. And then the other channel will also be giving me another time series, which is, let's assume this is the EMG signal, for example. Although it looks very bad, I admit that. Let's imagine that this is the second EMG signal from the second sensor. So what we typically do in EMG pattern recognition, we mentioned in one of the previous videos that we actually employ a moving window analysis approach. So I look at a window of EMG because I can't process the entire signal. I have to make quick decisions. So as soon as I accumulate some amount or enough amount of the EMG raw samples, I'll just process that and then slide the window to the right and keep moving forward. So imagine that you are looking at a window of the first channel and a window of the second channel. Let's imagine that the window length is 150 millisecond. So what you do over here is that you typically extract, let's say, for example, one very basic example, which is very well-known feature in EMG pattern recognition, which is the root mean square. So the first value you get over here, the first root mean square of the samples included in this window will be placed where? Here. Okay, so that's what you get as the first value. And then the second root mean square, or sorry, the first root mean square from the second channel will go over here. And then you slide your windows to the right, so you get the next window in this channel. Okay, and similarly, the next window in the top channel, you extract the root mean square, you chuck the first one over here, and you chuck this one at the bottom value, and so on. You keep sliding your windows to the right, filling in these values until you extract your features. So what happens over here is that you no longer have one dimension. You have a number of dimensions, which is typically defined by your input channels in this case. In my case, I had 2 sensors placed on the subject's forearm, and I extracted the root mean square features from the analysis windows from each of these, let's say, signals or channels, and I put them in the 2 dimensions, and then I run TCN on top of that. In this case, if I want to do something similar to my previous example where I had a kernel size of 3, so the kernel size is still made of 3 values. So that's 1, 2, and 3 values. So 1, 2, 3 across the first dimension, and 1, 2, 3 across the second dimension. In a similar fashion, the kernel size or shape will also change correspondingly, which means you will also have a kernel size of 3, and you will have actually 2 channels. So the process described in the earlier slide is repeated for every single input channel. And in this case, what you have is kernel size multiplied by the number of input channels. And that's the size that you have seen over here in our analysis. So let's say erase everything, take this one back, and let's continue our analysis. There are a few parameters that you need to get familiar with if you want to understand TCN characteristics or features. So the first one is causal convolutions. What does causal convolution mean over here? So for a convolutional layer to be causal, so for every single value I in the range from 0 to the input length -1, the ith element of the output sequence may only depend on the elements of the input sequence with the indices 0 to I. Let me explain. Imagine that you are looking at estimating the 10th element of the output sequence. In that case, to compute the 10th element of the output sequence, you are only allowed to look at the 10th element in the input sequence and the previous smaller elements in terms of the indices. So the 9th element, the 8th, 7th, 6th, 5th, 4th, and so on, depending on your kernel size that you have defined. So basically, for every element in the output sequence, its latest dependency in the input sequence has the same index as itself. What that means is that if you are looking to estimate the 10th element from the output, so the latest value from the input that you are allowed to use is the 10th as well from the input side. The other thing that you need to know is the equal length sequences. So to ensure an output tensor has the same length as the input tensor, we apply 0 padding. Let me explain with an example. So this is an example where I have a tensor, input tensor, and an output tensor. The length of the input tensor is 4. So you can see 4 sky blue cells, 1, 2, 3, 4. In a similar way, I should have 4 cells in the output tensor, or 4 elements, 1, 2, 3, 4. In this example, we said to calculate the element at the first position, I am only allowed to look at the first position from the input tensor and the previous ones. In this case, I don't have previous values. So what we usually do is we fill it with zeros, and that's called 0 padding. So we define in this case an example, hypothetical example with an input length of 4 and a kernel size of 3. If my kernel size of 3, it means to get the first element from the output, I need 3 input values. But I also have a condition that if I am calculating the first or the ith, I need to look at the ith from the input and the previous positions. So I don't have previous, so I'm 0 padding them. So you see over here, the orange has 3 arrows, 1, 2, 3, and then you go to the right, and then you can see that the maximum index you can get from the input side is the second. And then you also can use the first and a 0 that you have padded. Then you continue moving to the right, for example, for the purple. I will use the third as well, because that's the third position that I'm estimating. And in this case, I can use the second and the first because my kernel size is 3, and I don't need the 0 padding. And then you continue doing that as you keep going to the right. So I believe this is a very clear example. Now let's talk about the receptive field. What do we mean by receptive field? So one desirable quality of a forecasting model is that the value at a specific entry in the output depends on the previous entries in the input. Let me explain again. What this text is saying over here, as an example, if you are estimating the 10th element from the output, it's really desirable that if you can use the 10th element from the input and all the previous historical values before the 10th. And that can be any number, not only the 10th, but that can be any number. So basically, all entries that have an index smaller or equal to itself are usually desirable, like to include them, like to be included, all of them, when doing forecasting problems. How do you do that? This is usually achieved with the idea of receptive field, meaning the set of entries of the original input that affect a specific entry in the output. So in this case, if you want the maximum of these, so you like this receptive field should have a size of the input length, and in this case, we call this the full history coverage. Let me explain. So if this is an output tensor, and this is the last value in the output tensor, it's typically very desirable if you can include all the previous ones. So what is usually done, you can add few multiple hidden layers to actually allow you to do this in a nice fashion. So more generally, a one-dimensional convolutional network with n layers and kernel size of k has a receptive field defined by this equation. To know how many layers are needed for a full coverage, we can actually set the receptive field size to the input length I and solve for the number of layers n as based on this equation. So I want you to get the rough ideas about how TCN work over here, because my whole point of making this video is not yet explained. So my idea about this video is not that to explain the nitty-gritty details of TCN. You can Google that and find them anywhere, and so many different blocks available. But I have a specific topic in my mind that I will show you today about TCN. So another thing that you will typically hear about when working on TCN networks is the concept of dilation. So what does dilation mean over here? Dilation in the context of convolutional layers refer to the distance between the elements of the input sequence. So previously, when you had a kernel size of 3, we were actually taking adjacent, let's say, elements from the input tensor and somehow like manipulating them by multiplying by an implied kernel and doing the dot product to get the output. But what if that, let's say, dilation size is actually 2, not 1? So now you can see to compute the first value from the output tensor, you will also use the first value from the input tensor, and you need, let's say, 2 more values if you have a kernel size of 3. But because in this example, you say, I have a dilation factor of 2, you are not going to pad 2 more zeros only. You are going to pad 4 more zeros. Why is that? Because you need a distance between them, because you have a dilation size of 2. So you can see that there's a distance now between the arrows coming out from the different elements. They are no longer adjacent because of this dilation factor. Now, in a typical scenario where you want to have a full receptive field size, you might have a problem. Like, how do we achieve that? So basically, the problem can be addressed by increasing the value of D, the dilation factor, exponentially, as we can see in this example. So in the first layer, you can set it up to 1, you can set it up to 2 in the second, and 4 in the third, and so on. So the following figure shows a network with a length of 10, a kernel size of 3, and dilation base of 2, which results in 3 dilated convolutional layers for full coverage. So in this case, you are getting your full coverage that you are interested in. So to compute this value, you ended up calculating 3 from this layer and many others from the other layers, which means overall from the input, you have actually used all of them. There are other architectures or forms of TCN that you might also read about in the literature. For example, the one with the residual connection. What that means is that in this example, you have a, let's say, dilation factor of 1, a kernel size of 3. You are doing the same process across the layers, but you also have a direct connection from the input to the output as well. So there's an addition like over there. You can read about these different architectures and what they do specifically. So again, this is not what I made this video about. I'll dive into the important point for me on this video. That is related to the use of TCN in EMG pattern recognition. So let's get into that. This is an example or an illustration of an EMG signal with an analysis window that we typically employ in EMG pattern recognition. So again, as I mentioned before in this video and the previous videos, that we use overlapping windows, and we look at the EMG signal within the window and we extract features from it and then move the window forward and extract more features and build up our training data. So if I'm going to use TCN, and I mentioned previously that I'm extracting features. So in the case where you are actually applying TCN on features extracted from the EMG signal, assuming that the feature is so simple in this case, let me say it's an RMS, root mean square value. I don't want anything else. And I'm assuming something very simple. One channel with a kernel size of 3, no more, no even hidden layers. I'm not going to discuss more complicated. I'll show you the simplest form and what is the problem that I'm talking about and how that problem can be exaggerated when you have hidden layers. So the first window, you extract an RMS value. And if you like, this is the first element from the input tensor, and that will help you to get the first element from the output tensor. But because we said in this example, we have kernel size of 3, you need 2 more elements. And these are the zeros that you are going to pad. Then if you look at the window, I'm actually going to shift the window to the right, extract the new RMS value for the second element of the input tensor to help me get the second element of the output tensor. And for that, I will also need the first element from the input tensor and the previous 0 that I padded. Keep going to the right with your window, extract an RMS, get me the output, which uses the current RMS and the previous 2 values. Keep doing that until you extract a good amount of output elements in the output tensor, depending on the size, of course. Now, the figure on the left, I don't have any issues with it. It's very clear, it's very simple, and this is how the process is happening. Now, what I've noticed in a number of publications is that people are actually comparing the application of TCN on EMG versus the traditional classifiers. What do I mean by traditional classifiers? Like, for example, LDA, SVM, and many other like traditional classifiers. So assuming that I have an LDA classifier and I want to see how good is TCN versus LDA, like, are deep neural networks really effective? Are they really good? Can I actually use them instead of what the researchers have been using for the last 2 decades? I don't know. Let's see. So in LDA, the output only depends on the current input features. So LDA is not or does not really consider the historical dependency in the input. So assuming that it's the same window that you had over there and you are shifting it to the right as you did over here, extracting the same RMS values, every single output element depends on every single input element at the same index only. There's nothing more, no historical dependency again. So RMS2 will generate output 2, RMS3 will generate output 3, RMS4 will generate output 4. And if you don't know much about LDA, so you can watch this video on YouTube from TalStats about LDA and get some idea about it. There are so many videos. Watch whatever you want. Now, what is my issue over here? My problem over here is that you are not really comparing apple to apple or orange to orange. You are actually comparing an apple to orange. How is that? Because in the TCN side, on the left side, every single output value required the current input and the previous ones. While on the right side, every single output required the current input. So how does this make a problem? Well, if you haven't paid attention to the idea of the sliding window, so I said we are extracting features from each window. Fine. Let's assume that we are at this position. So this feature came from a window size. Let's imagine it's 150 millisecond. If I look at the features from the previous two values, it means I looked at window increments of 50 and another 50. So overall, in this side, you're actually looking at an amount of EMG signal that is like made up of 250 millisecond. While on the right, you are only looking at the feature extracted from the window of 150. 250 versus 150. This is not apple to apple. This is not orange to orange. So you have different sizes of input feeding the two models. Do you really care about that? Let's discuss that. Look, to be honest, there are, let's say, for me at least, there are majorly 2 points that I care about when developing algorithms. First is the performance. So if you manage to show me that while doing this, you get much better performance, for example, with a TCN than LDA, and you prove it with your statistical analysis, and you show me the p-value, fine, it's okay. Like performance-wise, you are doing good. Fair enough, I like that. But let's keep your comparisons fair as well in terms of the, let's say, the input that you are feeding to the two models. You are telling me that you have two models being fed by different size of input, different amount of data, and you're telling me one of them is better than the other. Okay, but you can't even compare in this case. Your comparison is not really valid. Why? Because you are not feeding the same input size to the same models. So let me explain it again. An EMG signal analysis window of 150 millisecond in my example, I do slide that to the right, and that increment value is 50, and I extract RMS1. Then I shift it a little bit further to the right by another 50. And from the new window, I extract RMS2. So you can see a window size of 150, you can keep shifting to the right. So if you look from right to left or left to right, the amount of the input to generate a specific output is considering the current window and the previous two ones. And the overall data, the overall EMG amount that you are actually looking at is 250 millisecond in this case. While in this other case on the right, which we assumed was an LDA classifier, the current output depends on the current input, which means the current 150 only. So you're comparing 250 versus 150, and this is something which is not fair. You are not comparing two models while being fed with the same amount of data. You are comparing two models while being fed with different amount of data. Performance-wise, you will do good. It's okay. We understand that. But let's say scientifically, you are not doing proper comparisons. Performance is one thing, but for you to do proper scientific research and publish this in very highly ranked journals, you have to have your experiments set up to be in the correct way, basically. So over here, the same analysis window size of 150 will actually generate the feature, and like at the input side, and the output side will depend on that only. So 150 versus 250, it's not apple to apple. So you are not feeding the models with the same amount of data. Let me explain this again to you in a different way, which is more intuitive, I believe. Let's assume me and yourself as a listener, we have an exam. Let's assume we are both students in one class and we have an exam. And the teacher, in this case, he's planning to get us the questions from the current page and the last 10 pages, or let's say the last 9 pages to make them all 10. So let's assume this is yourself, okay? You are allowed to read the current page and the previous 9 pages, okay? And in this case, he or she is allowed to read 10 pages at a time. This is the current page and the previous 9 pages. On the other hand, there's another student, which could be you or me, which is only allowed to read the current input page. So in this case, I don't have historical context. I can't look at the previous values. I'm only allowed to look at the current one. I'll only read this. What if the questions came from the previous 2 pages? Well, I didn't see it. Good luck. I don't know what you're doing. Of course, you will achieve better than me. You will get better marks. Is this fair? Well, you do get better marks in this way. There's a good potential that you get way better performance than me, but it is not scientifically accepted way of comparing the performance of 2 students because they are being fed by different amount of input. So he or she is allowed to read only 1 page, and he can't do as good as subject A. Of course, you're feeding them with different input. So TCN was designed with the ability to include temporal evolution. So when I have discussions about TSN with my colleagues, one thing that I always get is that, okay, why should I care? Performance is good. As long as the performance is good, the accuracy better, my product will be better. I will make the prosthesis work in a more accurate way. Why should I care about the fairness of comparisons? You should, and I'll tell you in a while why. So LDA SVM only look at one window at a time. Okay. So now why should I care about that? Well, first of all, let's discuss something important. Which model do you think is computationally more feasible? So if you are an engineer implementing or developing a controller, a prosthesis controller, and you need to chuck your algorithms that you have designed, you need to put them in that controller somehow. And then you have the TCN on one side and LDA on one side. Which one do you think is more feasibly implemented? Well, I'll surprise you. I'll tell you with many cases, like with the big companies especially, like from my experience, the simpler the methods, the more chances that we got at the time to include these methods in the products. Like if you can come with more complicated products, more accurate products, but at the end of the day, it's the simple one with less computational costs that are actually being included in different product. So computational complexity is also a very important factor to look at. All right. So obviously LDA is the winner because it's less computational. Like basically it's way less computationally costing that TCN, especially when there are multiple hidden layers with TCN and large kernel sizes and receptive field sizes. The other thing is the performance, as we discussed. So yes, performance-wise, you can do better with TCN, or maybe not. I don't know, because you didn't show me in your experiment. If you feed the same amount of data to LDA, what would the LDA do? So in many of the papers I'm reading, they say, oh, we used an analysis window size of 200 milliseconds, and we did the increment like 10, and then we ended up using the current window and the previous 20. Hello, what about the amount of data that you're feeding? And then they say, oh, this performance is much better than LDA. Okay, but LDA is looking at one window. You're using the current and the previous 20. How is that fair? So performance-wise, you may or may not be, like, let's say, doing better than classical classifiers. You have to show us both results, both tables of results, and do proper sets of comparisons. So I honestly can't tell if you are doing better than classical approach or not if you don't show me these results. And in terms of the performance, there are so many metrics that you can use to evaluate the classification models like sensitivity, specificity, accuracy, balanced accuracy, and so many other factors or measures that you can use. And there's another aspect of the comparison between TCN and LDA, specifically targeted for the problem of EMG pattern recognition. So let me explain this. You know that with EMG pattern recognition, what we are doing is gesture recognition, hand movement recognition. While I'm doing hand movement, what am I doing? I'm looking at the EMG signal and I'm looking at 150 millisecond only. So if I am trying to open my hand or close my hand or pronation movement or any other movement, you are giving me access to only a tiny amount of EMG signal, which means like looking at the microscopic level of the hand movement, which is very tiny amount of data. It doesn't tell me how the hand is going in which direction or which muscle is going to work and how active it is. So if you don't show me that, how do you expect me to tell you that this is the actual correct movement? This is from the perspective of LDA. On the other hand, with TCN, you're saying, oh, use the current like, let's say, snapshot of the EMG signal, use the previous 10 or 20 or whatever. And of course, in that case, you can have better performance because you are looking at more representative part of that movement. So you are looking at bigger size of that movement. If you are doing pronation, for example, our hand open or hand closed, you already got a good amount of data to tell you what kind of movement it is. Another aspect related to the computational complexity, which I've actually quoted for you from one of the recent papers, it says, training deep learning models requires a significant amount of memory for the weights, activations, gradients, data batches, workspace, and which can be hundreds of megabytes or even gigabytes. So to put one of these deep learning models into a online, let's say, controller, you could be looking at hundreds of megabytes or even gigabytes worth of memory requirements for something like a decent convolutional network. While LDA is like very traditional classifier, the computational cost is much less than that. So you can refer to this paper, Survey on Device Machine Learning and Algorithms and Learning Theory Perspective, and read more about the computational costs over there that you can anticipate while using deep learning models on device. So what do we need to do in this case? Well, we need to give a fair go for the algorithms, just like we give for a human in Australia, specifically because we always talk about the fair go for everyone over here. I'm sure it's the same on your side of the world as well. So how do we give a fair go for the algorithms? Well, enlarge, like one point you can do, enlarge the window size for LDA. Make sure that you are looking at equivalent amount of the EMG signal when you are feeding that to the LDA, and the same size when you're feeding to the TCN. In that case, you are actually feeding both models with the same like EMG amount or like amount of EMG data, basically. The other thing which you can do is that, okay, keep the window size as it is, but you can apply majority vote at the output of LDA to smooth the output. That's another way if you want to like fair analysis. So another alternative, which is to use a variant of LDA. So people have been developing different versions of the classical LDA. I'm sure you will find a version that actually allow you to look at the temporal evolution as well, something similar to TCN, and compare the two of them in that case. Another thing that you can do is use a feature extraction method that when extracting the features from the current window also includes the, let's say, impact of the EMG signal from the previous window. One such algorithm in my GitHub profile is the FTDD, feature extraction method. So when extracting features from the current window, we fuse that with the features extracted from the previous window, and we give you the features. So this is where you get, for example, I'm just saying, for example, it's not the same. So for example, your RMS that represent that current window, and feed this to the LDA and let the LDA decide. So there are so many different ways for you like to keep your comparisons fair. So just some credits for TCN illustrations. I get it like the illustration, I get it from these blogs by the same person. And there's also a paper like denoted for you over here, which is worth reading, actually. Very nice paper. So again, my whole point for today wasn't about how really just how TCN is working, how to get better performance or something like that. No, it was about the use of TCN for EMG pattern recognition and how some experiments run by different researchers are being done. And from a perspective of the reviewer, who's actually trying to keep the, let's say, high quality of journal publications, I have to make sure that you're not only considering performance, but you're also considering other factors that we look at, for example, the computational cost. So in this case, I showed you that many examples, I'm not saying all of them, I'm just saying many examples are out there where people actually are doing this and feeding different amount of the EMG signal into the two different classifiers, the traditional versus the recent deep learning models. And then the claim is, oh, deep learning models are better. They are better within the context of your experiment. You can avoid that and design proper experiments by feeding the same amount of data. And that's how, in my humble opinion, that this type of experiment should be made. Thank you very much. And that was all for today.